Hello, everybody. Thank you so much for joining us for another live webinar session here with EE Tech and allaboutcircuits.com. My name is Jason Montgomery. I'm going to be the moderator for this session here. Let me tell you about what we're talking about here today. The title of our session is Eliminate Arcing in 48-volt Boardnet Systems with a New eFuse Design, and this is brought to us with Vishay Intertechnology. Our presenter today is Scott Blackburn, who's a manager of automotive field applications. He received his bachelor's and master's degrees in electrical engineering with a power electronics focus from the University of Toledo in Ohio, and later an MBA from Bowling Green State University in Ohio. He initially worked as a design engineer in the aerospace industry, and then made the jump to the automotive world, where he worked for Ford and the Dana Corporation. He's been with Vishay for over 13 years, and he's responsible for application engineering and business development in the Americas for all the automotive products. So I think this is a really great session we've got in store, everyone. Really want to thank everyone for coming and joining us here today. And Scott, thank you for being here as well.
All right, thanks, Jason. That was a very nice introduction. Good morning, good afternoon, maybe even good evening to everyone. I appreciate your showing up for this webinar. I hope it'll be interesting. And like Jason mentioned, we're going to talk about a unique reference design that's been developed by Vishay, and it can be used in any 48-volt load applications up to 200 amps. But before we get into that, I just wanted to maybe give a little background. So we're going to talk about the 48-volt dual Boardnet. Now, this is still an emerging technology, but it's growing quickly and will continue to do so. There are already vehicles on the road with 48-volt systems. They've been around in Europe for a few years now, and they're making their way to the United States as we speak. So when we talk about a dual Boardnet architecture, we're talking about vehicles with both a 12-volt bus and a 48-volt bus. And as I said, they're becoming more popular. We're going to need new modules and components to support these designs. So for example, you'll see there on the screen a high-power bi-directional 48-volt to 12-volt DC to DC converter. You're going to need that to transfer energy in either direction between the 12-volt battery and the 48-volt battery, depending on what's going on in the vehicle. Now the 12-volt bus, that'll continue to support the low-power loads, like the interior, exterior lighting, powertrain control modules, the infotainment system, any other basic control modules or functions. And there's already plenty of infrastructure in place for those type of systems, so we'll leave those on the 12-volt bus. And the 48-volt bus, now that's created for the new higher power loads in order to reduce the currents, keep the cost of the wiring and other components reasonable. And these loads would include like electric power steering, air conditioning, engine cooling, electric turbos, any parallel hybrid inverters for like start-stop or traction assist. So as we develop these new systems, the current requirements are going to continue to increase for both the 12-volt and the 48-volt vehicle systems. So there's going to be a growing need to replace the conventional mechanical relays with new methods for, purposes of life expectancy and safety. Now, these mechanical relays for connecting and disconnecting high current 12-volt loads, they've been the traditional solution in vehicles for many decades. However, with the addition of high current 48-volt loads, the same type of component cannot necessarily be used due to the increased voltage for the following reason. So in any 12-volt system, there's an electric arc that's created between the two contacts when a relay first starts to open, when there's voltage and current present. However, this arc will extinguish itself in a matter of milliseconds as that distance increases between the contacts until that circuit's completely open, since the voltage isn't high enough to keep bridging that air gap. And this is just a real simple video to illustrate the arc that's created when you separate those two contacts or wires when there's voltage present. As long as that arc continues to burn through the ionized air, the ends of the wire, the contacts in the case of a relay, they're going to lose some of that surface metal during the process. And this, is obviously going to reduce the life of the contacts anytime this arc's allowed to occur, which is pretty much every time that relay is open during the life of the vehicle, which could be hundreds of thousands of times. So in a 48-volt system, it's a much worse situation. Due to the increased voltage, the arc that's created when you open those contacts is no longer self-extinguishing unless there's a much larger distance used to open that circuit. And even if that larger distance is achieved, there's exponentially more energy that needs to be interrupted. So, it's still possible to use mechanical relays, but they get larger, they get more expensive with the additional design considerations or some type of arc suppression circuit. And even then, life expectancy is still reduced due to that extra contact wear and tear due to all that extra energy. Okay, hopefully you guys have had time to answer that poll question. I'm going to move ahead here and keep talking. So we're going to get into the design now. In order to maintain the life expectancy and safety requirements, as I talked about for the vehicle, we've developed a unique electronic switch and resettable fuse that can be used in any 48-volt high current load application. And we're going to spend the rest of this presentation talking about the details. So this design's been put together to switch loads up to 200 amps at 48 volts, and it works with a standard double-sided FR4 printed circuit board with passive cooling, and there's no external heatsink required. And this design also features a pre-charge function and continuous current monitoring for control and protection, which I'll talk more about later in the presentation. Okay, to give you an idea of the basic architecture, this schematic shows a simplified version of the power stage. So the 48-volt battery inputs on the left, the output voltage to the loads on the right, and I'll go through this in much more detail during the rest of the presentation. Just to give you an idea of the layout, you can see the top and the bottom side component footprints, and I'll be using these layouts to point out some more details as we go through the rest of the presentation. And you can see there in the red boxes, the main power stage components are located on the left side of the board on both the top and the bottom, and most of the control circuitry is located on the right-hand side of the bottom of the board, there in the red box as well. All right, in order to switch these very high currents of up to 200 amps safely and efficiently without damaging those components due to thermal stress, we've designed the power stage with discrete high current Mosfets. This design features two sets of switches, and they're labeled TR2 and TR3 in the schematic there in the red boxes, which are connected in a bi-directional arrangement to handle the high load current. And note that without this type of connection, the current could flow back through the Mosfet body diodes to the battery when the load's deactivated, so you need this switch setup. And due to the very high currents involved, we're actually using 10 Vishay Mosfets. In this case, it's part number SQJQ160E, which I'll talk about more in a few minutes. They're connected in parallel for each switch in order to minimize the resistance and the power dissipation. And using this arrangement, the total losses can be limited to under 10 watts at 200 amps, which is pretty impressive considering we're outputting nearly 10 kilowatts. All right, taking a look at the layout again, you can see those 10 parallel connected Mosfets for one switch on the top, and then the other 10 that are connected in parallel for the other switch on the bottom side. And they're all situated as close together as possible. We want to minimize stray inductance or capacitance. You also want to make sure the current's shared equally. So we want to have them, as close together as possible so they'll be roughly the same junction temperature. And as I mentioned a minute ago, that SQJQ160E that we're using in this design, this is a trench technology Mosfet. It's in our PowerPack 8x8L package. And this 8x8 millimeter package features a bond wireless clip construction, which gives you some benefits in several areas. First of all, it results in an extremely low junction to case thermal resistance, approximately 0.25 degrees C per watt for this package, which allows for a much improved thermal transfer compared to a wire bond construction. And this bond wireless construction also allows for very high pulse drain currents, which is critical when you have overload or short circuit conditions at the load. And one more point to mention is this gull wing lead frame that you see here provides improved board level reliability, which is basically the ability to maintain solder joint integrity over the life of the product as it gets subjected to thousands of thermal cycle events. So in this design, we used a 60 volt part with a drain to source resistance of 0.8 milliohms. Each were selected, they were selected because they're very close to the 48 volt battery, and no more than 58 volts will be seen worst case. But, to protect these Mosfets from any transients induced by the load through a lengthy wire harness, transient voltage suppressors are required, and I'll detail those later in the presentation. And even though it wasn't used in this design, I also wanted to mention real quickly that we have a top-sided or reverse cooling package that you see there at the bottom of the slide. It's available for applications where the heat needs to be removed from the top side through a separate heat sink, rather than down through the printed circuit board to the heat sink, using thermal vias in a traditional configuration. Okay, a little more detail on driving the parallel power Mosfets that I just discussed. Sometimes, small details like choosing a gate resistor get overlooked, but in this design it's fairly important due to the several amps of peak current that's required to turn on these 10 Mosfets connected in parallel. Using a thick film resistor might be a first thought when picking that gate resistor, since the average power is very low. However, it's the pulse capability that's the key consideration in this type of application. Most standard thick film resistors don't handle large pulses of current very well. They'll eventually degrade and even fail. So therefore, you need to look at another technology when you've got these high pulse current applications. So, in this instance, we selected a thin film technology, specifically the MMU series from Vishay. This is available in 3 sizes. This is in a cylindrical MELF package, and in this design we used the 0102 size. It has a very high pulse capability, which is important in this application, as I mentioned a few minutes ago. Due to that extra amount of surface area compared to a standard flat SMD package, which you can see in that diagram there. So it's a very stable technology, which means that the resistance value will not drift very much over time and temperature. And just for reference, it's available in a pretty wide range of values. Okay, in order to protect the vehicle wiring and prevent greater damage to the load in case of a short circuit, we monitor the load current continuously using a shunt resistor, which is labeled R2 in the schematic there. And when a predefined overload current is detected, that controller can quickly disconnect the battery from the short-circuited load with minimal time delay due to a hardware comparator circuit that was used in this design, which I'll talk about in more detail in a few minutes. However, this short amount of time until the load's deactivated, those Mosfets can handle a considerable amount of overload current due to that high pulse drain current capability that I talked about a few minutes ago. And in addition, under normal operating conditions, that continuous currents used by the vehicle's body control module, some type of serial interface or the CAN bus to monitor the state of health of the battery, that is like the charge level, the remaining lifetime, things like that. Okay, as you can see from a more detailed view of the schematic, 4 current shunts were connected in parallel to minimize the power dissipation. In this case, Vishay WSLP 3921 was selected, each with a 300 microohm value, which results in a total shunt resistance of only 75 microohms. And then a differential voltage measurement is taken across that resulting shunt and then fed into a current sense amplifier. Okay, here's a detailed view of that current sense amplifier that's used to take that very small voltage in millivolts that's measured across the shunt and amplify it to a voltage level that can be used for control and protection. In this case, that amplified voltage is fed into both the microprocessor for current monitoring and also into that comparator circuit for overcurrent detection, which again I'll talk about more in a few minutes. All right, taking a look at the layout again, you can see the 4 current shunts in relation to each other and to the power Mosfets. They're located in tight proximity to each other, 2 on the top, 2 on the bottom, and also in relation to the input terminal and the Mosfets. Once again, this minimizes any stray inductance or capacitance, and this symmetrical layout provides for current sharing between the individual shunts. All right, I wanted to take just a few minutes to explain why a current shunt technology was selected for this design. So in most high current applications like this one or maybe a motor drive, the current needs to be monitored for control purposes or overload protection. And there's typically 2 methods that are used for this, either a resistive current shunt like this or a Hall effect sensor. Now, a Hall effect sensor is relatively simple to implement as a turnkey solution compared to a current shunt, which, as you've seen, requires some additional feedback circuitry, but it can suffer from the following disadvantages. It can have low linearity over a wide current range. There could be some offset error due to wide variations in the temperature. There can also be excessive measurement latency and bandwidth limitations, depending on the switching frequencies being used. And a Hall effect sensor will also saturate when its current range is exceeded, and it won't be able to provide an accurate measurement. And in addition, a Hall effect sensor requires a separate power supply for operation. And finally, the overall system cost tends to be somewhat higher, for a Hall effect sensor, considering everything. One more point, customization of a Hall effect is usually not cost effective or even possible. Whereas a Vishay current shunt, it can be configured to meet the mechanical constraints of the system, either in one of these many standard packages that are shown there on the diagram from 0603 to 5931, or a customized version of that larger 8518 shunt that's shown there as well. Okay, as I mentioned before, the WSLP 3921 was selected for this design. This is a Vishay power metal strip design. It features an all-metal welded construction. So in addition to the benefits described in the previous slide, it can also handle very high pulse currents that can occur during overcurrent or short circuit conditions. This WSLP 3921 offers the lowest possible resistance values of this series down to 100 microohms, and it also offers the highest power rating of up to 9 watts in this package. The WSLP 5931 could be used if even higher power ratings are required, up to 15 amps. And that raised element package, as you can see highlighted in the red box there, that also lowers the resulting hotspot and keeps it away from the printed circuit board, which may not be able to handle the same operating temperature as the shunt. And if needed, the WSLT 39 series, that extends the temperature range up to 275 C. So those are for very high ambient temperature conditions, when you're under hood, or maybe just even for some added headroom with the necessary derating curve. Okay, jumping back to some more details on the current sense feedback, I mentioned a comparator circuit that was used to detect an overcurrent situation. In this design, the amplified current sense voltage is continuously compared to a preset reference voltage that would correspond to an overcurrent event. And then when this level gets exceeded, the comparator trips, and that overcurrent signal is sent to a microprocessor interrupt, and then those main load switches are immediately opened. in order to make sure that reference voltage and those trip points don't drift over temperature and time in the field, a match pair of resistors should be used for any op-amp circuits. And even if thick film resistors with exactly the same initial value were used in this case, those resistance values are going to drift significantly when they're soldered initially, and then with temperature, with time in the field, and that shift could even possibly be in opposite directions, which makes things worse. And therefore, a thin film technology should be selected for this type of circuit application. So again, in this design of the Vishay ACAS precision thin film resistor array was selected. And this array is available in either a 2X or a 4X configuration. And you can get resistances of any value, up to a 1 to 100 ratio. And due to the thin film technology and the fact that the individual resistance elements are manufactured on a common substrate, you can get very impressive individual tolerances down to 0.1%, and matching tolerances even better down to 0.05%. In terms of the relative temperature coefficient, you can get down to like 5 ppm tracking between the resistors. Another feature of this design prevents a common issue that occurs when first connecting the battery to the load during vehicle startup. That is the potential inrush current due to any uncharged capacitor banks in the load. Now, if this resulting high peak current's allowed to occur, downstream components could be damaged and the battery lifetime could even be reduced. Therefore, a pre-charge circuit must be used to limit that inrush current to an acceptable level. In this case, a Vishay Mosfet labeled TR1 in the schematic there in the red box, a Schottky diode labeled D2, and a Vishay power resistor labeled R1 are used to limit the inrush current to a maximum peak of about 5 amps at 48 volts. So before energizing the load, TR1 is switched on for a predefined time, for example, 10 milliseconds. And then that output voltage, which is labeled X3 there in the schematic, is monitored. And if that output voltage is not reached, roughly 90% of the input voltage after that time, the process gets terminated with the assumption that there's a short circuit in the load or the wiring. And if that output voltage has reached the appropriate level, then TR1 is switched off, and TR2 and TR3 are switched on, as I described before, to energize the load. And just also note real quick that Schottky diode is used to prevent backflow of the current through the Mosfet body diode when it's in the off state. All right, as you can see from the layout, the main pre-charge components are located on the top side of the board near the other power components. Both the Mosfet and the Schottky diode were sized to handle that 5 amp peak current for 10 milliseconds, including some safety margin if you were to have extended pre-charge times or maybe repeated pre-charge attempts for whatever reason. The power resistor used for this pre-charge circuit was a Vishay D2TO20 resistor. It's a thick film technology in a D-squared pack surface mount package. And it's designed for very high pulse load applications. The nominal power rating's 20 watts at 25 C case temperature, but that needs to get derated for higher operating temperatures. However, in this design, since this pre-charge circuit's basically a pulsed event, care must be taken to make sure the peak power rating of the resistor doesn't get exceeded during that time. And in this case, a 10 ohm value is used for that 10 millisecond pulse, which is safely within the capabilities of the power curve that's shown here, and it's also in the data sheet. Okay, just a quick comment on voltage sensing, since it's required in the pre-charge circuit to monitor the output voltage. And it's also, used in several other places in the design, the input voltage, for example. And again, in order to make sure the voltage dividers used to make these measurements don't drift over temperature and time in the field, and then, that's going to throw off your measurement. A match pair resistor should be used for any critical voltage measurements that are used for control or protection. Therefore, that thin film technology should be selected again for this type of circuit application. And as in the current sense feedback circuit, we use this ACAS precision array. This time it's a 4X configuration. Okay, in order to protect all of the downstream components in any electronics module from high voltage or high energy transients that get induced, either on the 48 volt or the 12 volt bus, some type of transient voltage suppressor is typically utilized in most designs. This type of device will absorb that energy from the unwanted transient pulse and then clamp that resulting waveform to a level which is no longer harmful to the remainder of the components. So in this design of the Vishay XMCK24CA and a 5KA SMC30A transient voltage suppressor connected in series, those are labeled D1A and D1B in the schematic there in the red box, and located on the output to protect the components against transients from the vehicle load. The location of these transient voltage suppressors is very critical when you're looking at the layout. In this design, since we're trying to protect all of the components on the circuit board from transients that might get injected from the load, the devices need to be located as close as possible to the source. Therefore, they've been placed directly between the output terminal and the power ground connection, as you can see there. All right, that XMC7K24CA transient voltage suppressor selected for this design, this actually features a new Vishay X clamp or snapback technology. Has an extremely low clamping voltage ratio for suppressing those transients to lower clamping voltages than conventional TVS devices. It features a 24 volt working voltage. It's in a bidirectional arrangement, has a very high pulse load capability, up to about 7,000 watts for a standard 10/1000 microsecond pulse, all in an SMC package. And this can also be paired with other TVS devices like we did in this design to achieve other working voltage levels. All right, as you can see from the current versus voltage graphs on this slide, that X-clamp suppressor has a much steeper slope compared to a conventional device, which results in a much lower clamping voltage for the same level of peak current. In order to obtain other working voltages for a specific application, this part can be connected in series with another transient voltage suppressor like I mentioned. For example, the Vishay 5KA SMC family. And in this particular design, again, we used that XMC7K24CA. We paired it with a 5KA SMC30A, and this gives you a 54 volt working voltage with a very low clamping voltage capability. All right, in order to provide power for all the control circuitry that you saw there in the beginning, a 5 volt regulated power supply was required. And to minimize space, the space that was required, we used an integrated synchronous buck converter, which I'll describe in more detail in the next couple of slides. Okay, looking at the layout, you can see that only a very small section of the printed circuit board on the bottom side was required for the complete power supply, with the exception of the storage inductor, which was placed on the top of the board there in the red box. All right, here's some more details on the synchronous DC to DC converter, which is a Vishay Microbuck series product. The actual part used in this design is from a commercial family, but we're in the process of releasing an automotive grade version as shown here. It's an integrated multi-chip design that incorporates the control IC and both of the power Mosfets, all in a 5x5 millimeter package. The only other components required are the storage inductor, which I mentioned, an output capacitor, and then some small resistors and caps to set some of the control parameters. It has a very wide input range from 4.5 to 65 volts. So it can be used in just about any automotive application, either on the 12-volt bus or the 48-volt bus. The output voltage is adjustable to any value down to 0.8 volts. And there'll actually be two output current options available, 6 amp and 10 amp. It's also a very highly configurable system with the switching frequency being adjustable anywhere from 100 kilohertz to 2 megahertz. The soft start and the current limit functions are adjustable as well. Samples of these new automotive grade products are planned for Q4 this year. All right, I also wanted to spend a few minutes on the details of the storage inductor that was used for the power supply. In this case, a Vishay IHLP 2525 22 microhenry inductor was selected, and that's based on the criteria that's described in the microbuck data sheet. So the Vishay IHLP family of inductors come in a wide range of sizes, from the IHLP 1212, which is 3 millimeter by 3 millimeter, up to the IHLP 8787, which is 22 millimeter by 22 millimeter. They're available in various heights. They feature a powdered iron construction, which provides a soft saturation, which I'll talk about in more detail in a few minutes. The low profile package and the wide terminations, they give you excellent mechanical shock and vibration performance, especially in engine mounted applications. The IHLP inductors also exhibit very impressive current ratings. For example, if you can see on that chart there, a 1 microhenry IHLP 8787 is rated for continuous operation at 69 amps, which is defined as the DC current that will cause an approximate increase in temperature of 40 degrees C. And these inductors can also be operated up to 180 degrees C, which I'll also talk about more in a few minutes. Okay, so this IHLP technology was originally created and patented by Vishay. It features a very unique construction if you haven't seen it before. The high temperature copper magnet wire is wound first, and then it gets ultrasonically welded to a copper lead frame that's plated with nickel and tin. You can see in the diagram there. And then a proprietary blend of low loss iron power gets pressed around that winding and lead frame at a very high pressure. And then that resulting assembly is cured at a specific temperature, which results in a very compact inductor. There's no wasted space, since an air gap or a bobbin's not required, as you might find in the construction of a typical inductor. The copper wire and the lead frame carry current, and the powdered iron carries flux. So that results in the most efficient inductor possible in terms of the volumetric density. And in addition, since that winding is completely contained within that magnetic material, you basically get a magnetically shielded inductor without having to add a separate shield, as you might find in other inductors. And also, due to this composite construction, these inductors exhibit ultra-low buzz noise. Okay, in terms of the saturation characteristics that I mentioned a few minutes ago, the IHLP compared to a standard ferrite inductor, there's a drastic difference in performance. The red curve illustrates a typical ferrite inductor, as that current is increased for a given inductance value. That curve is very flat up to a certain current level, known as the saturation point, at which there's a significant drop in the inductance. And as that current continues to increase, the inductance continues to drop until that inductor behaves more like a resistor, which is obviously not the desired result in most power supplies or filter designs. But in contrast, the blue curve, which illustrates the typical performance of an IHLP inductor, that current's increased for a given value, and inductance decreases very slowly, pretty much a linear rate, but it never reaches a hard saturation point like a ferrite. And this is a significant advantage in performance, knowing that your inductor will continue to behave like an inductor over the entire range of current. It also allows the power supply or the filter to handle high transient current spikes without saturation, improves the ruggedness and reliability of the system. It should also be noted that, even though the powdered iron IHLPs do not hard saturate. We still define a saturation current rating in all our data sheets. Since the inductance does increase to some extent as the current increases, we define saturation as the DC current that will cause the inductance to drop to approximately 20% of its initial value. And we also provide the inductance versus current graphs for each value on our data sheets. And furthermore, a ferrite inductor is very sensitive to temperature. As your operating temperature is increased, or the ambient temperature, that same red curve is going to shift to the left, and it's going to continue to do so as long as that temperature keeps increasing. And it's going to result in an even lower current saturation point, which typically results in using a larger, more expensive inductor to prevent saturation at the worst case conditions. Now, the IHLP inductors, on the other hand, do not exhibit any temperature influence whatsoever with regard to saturation. So that same blue curve for a given inductance value will look the same whether the inductor is being operated at minus 40 C, room temperature, or even at the maximum operating temperature. Again, this is a huge advantage when you're designing a power supply or a filter. All right, one more benefit of the IHLP family of inductors is the material options that are available. So when this technology was first created and released for production, there were only two material choices available, both topping out at 125 C with regard to the maximum continuous operating temperature. So that -A1 material that you see there was optimized for very high frequency operation, up to at least 5 megahertz. So it exhibits the best saturation performance, lowest AC core losses possible. The -1A material that you see there, on the other hand, was optimized for the lowest possible DC resistance. Still has good frequency characteristics, up to at least 2 megahertz, and the AC core losses and saturation performance are still reasonable. But in the years since the inception of this technology, there's been continuous improvement in the iron powder in terms of the temperature and the frequency response. So now there's two more options with regard to maximum continuous operating temperature. That -5A material can be used up to 155 C, and the -8A material can be used up to 180 C. And both of these materials have been optimized in terms of the core losses and the DC resistance. So that resulting frequency response and DC losses they're just a good compromise between the -A1 and the -1A materials. All right, there's a relatively new product that's also worth mentioning. It's being quickly adopted by many of our key automotive customers. We call this the Vishay IHLE. It's our standard IHLP with the 155 C material. Been outfitted with a shield to contain the electric field emissions. And if you remember back to the construction of the IHLP, the winding's completely contained within that magnetic material, so you effectively get that magnetic shield for free. However, the construction doesn't contain the electric field, and nor does any other type of inductor for that matter, since that's the function of a capacitor. Therefore, during radiated emissions testing for EMC compliance, the inductor tends to be the chief offender in many cases when the test limits are exceeded. And, there's several potential remedies, which include an external shield over the inductor or the entire power supply, maybe using an appropriate enclosure as a shield, or just trying a new circuit board layout. All of these methods can add significant cost and complexity and time, depending on how severe your problem is. But in contrast, using an IHLE from the beginning of the design, or swapping out an IHLP if the printed circuit board has already been laid out with the extra 2 terminals for the shield, it can be a very quick and cost-effective solution. So the results are obviously going to vary from one design to another, but reductions up to 20 dB in the electric field when measured at a distance of 1 centimeter above the center of the device have been achieved. The IHLE is currently released in the 25-25, 32-32, 40-40, and the 50-50 sizes that you see there in the big circle, with the smaller 20-20 size coming out later this year. All right, I'd like to cover just one more topic before wrapping up this presentation. Although the power MOSFETs are sized to handle the 200 amps of load current, still a good idea to monitor their operating temperature in case of unforeseen circumstances, such as an excessive ambient temperature or maybe fluctuations in the load that could cause excessive heating in those MOSFETs. Therefore, Vishay surface mount NTC thermistor was selected to monitor the temperature. As you can see on the layout, the thermistor is placed as close as possible to the group of power MOSFETs on the top of the board. Therefore, the heat generated by the MOSFETs will make its way through the printed circuit board and result in a corresponding temperature rise in the thermistor. The feedback circuitry required for the thermistor is shown on this schematic. Voltage dividers set up with the thermistor and some biasing resistors off of a precision voltage reference, and then that voltage gets fed back into the microprocessor for monitoring. The Vishay thermistor selected for this design is from the NTCS family. They can operate up to temperatures of 150 C. They're glass coated and protected. They also have a flexible polymer termination that's going to resist board flex and solder cracking due to thermal cycling. And this design in 0805 size was selected, but they're also available in an 0402 and an 0603. The available 25C resistance values range from 2K to 680K. And the B value ranges from 3420 to 4125 Kelvin, and you can get tolerances down to plus or minus 1%. All right, well, in summary, a new electronic switch and resettable fuse design has been presented that could be used in any 48-volt applications up to 200 amps. This design also featured a pre-charge function to limit any potential inrush current to an acceptable level, and continuous current measurement for use by the vehicle's body control module to monitor the state of health of the battery. And this concludes our presentation for today. I thank you for your time. I hope it was informative and relative to things that you're working on, and also hope you keep Vishay in mind for any discrete components for your new designs. And we are going to put up one more poll question here before we finish. And while we're doing that, I am going to turn it back over to Jason, and I think we're going to have a Q&A session here.
All right, Scott, thank you very much. As a reminder to everybody, I know lots of you know this already based on the number of questions that we have coming in, but if you have anything on your mind right now, it's a great time to use that Q&A box, that Q&A widget to submit some questions while we've got Scott on the line here. So Scott, let's go ahead and just dive in. We've got a lot to go through. First question people want to know, someone's asking, will this design be available to customers?
Yes, actually, we're planning to release all of the design details as a free download. So that would be the schematics, the Gerber files, the bill of material, test results, and we have them complete. And those should hopefully be available in the next month or two.
Okay, sounds good. Now, can this design be scaled down for use with lower current loads?
Yes, for sure. This is definitely a scalable design. So obviously the control circuitry would remain about the same, but you could decrease the number of MOSFETs that you had in parallel there in the current shunts, which would decrease your overall size of the board and the cost. You know, for example, if you only needed to control a 100 amp load, you could just use 5 MOSFETs in parallel for each switch and maybe only 2 current shunts. So yes, definitely scalable.
All right. Another question that someone's got here, how do you make sure that the 10 MOSFETs connected in parallel are sharing the load current equally?
Okay, yep, good question. I kind of mentioned this a little bit in the presentation, but I mean, you always want to make sure the layout's as symmetrical as possible. You know, those high current traces that you have, you want to keep them similar length just to keep the resistances similar. But even if you have some small differences between MOSFETs themselves or the traces, just because you can't quite accomplish it with the layout, those MOSFETs are going to self-regulate. So basically what I mean by that, if one MOSFET starts hogging more current than the others, its junction temperature is going to start to increase, which will in turn cause the RDS on to increase, which is then in turn going to cause that current to start to decrease, so that it starts sharing again equally. So yeah, you pretty much have good current sharing, and that's important in this design, but it kind of takes care of itself, so to speak.
Got it. Thank you, Scott. Another question, someone noted that you mentioned thick film and thin film resistors a few times. Can you walk through the difference between those?
Yep, sure. I probably should have mentioned that, but yeah, so basically a thick and a thin film refers to the resistive material that's used. So a thick film uses a paste, which is basically screen printed on the resistor, and it's relatively thick, as the name suggests, but not very uniform. However, like a thin film resistor, that material is actually sputtered onto that resistor in a vacuum. So you get a nice, thin, uniform coat, hence the name thin film. And you can think of it kind of like the difference between brush painting and spray painting. One gets put on pretty thick, the other very thin, but also the thin one gets put on pretty uniformly. They're also trimmed very differently to their final resistance value. Thick film resistor gets either one I-shaped or one L-shaped cut to get to that final value, where if you look inside a thin film resistor, there's multiple meander cuts from each side. That eliminates hot spots, allows better current flow, pulse handling. So basically, you throw that all together. The differences in manufacturing. Basically, a thick film resistor is typically a 1% tolerance at best. Its value is going to drift pretty significantly over time and temperature, and it really doesn't handle pulse loads very well due to the way it's trimmed, like I described. And then a thin film, on the other hand, that could have tolerances down to 0.02%. So that initial value is not going to drift over time and temperature very much, and like I said a few times, it handles those pulse loads with no issues. So that's basically the difference.
All right, thank you, Scott. Let's see here. Next question. What's the advantage of having a unidirectional and a bidirectional TVS connected in series compared to a single TVS diode of the appropriate voltage?
Yeah, good question. So, in this design, like I mentioned, we used two in series. The one was that snapback TVS that I talked about. And the reason we use two is right now we only have that in a 24-volt value, which is very common for a 12-volt system. So we put another one in series. And since one of them's bidirectional, the other one doesn't need to be. It could be, but it really doesn't add any value. So that's the main reason. Typically, you can get away with one TVS in a design. Maybe I should mention real quick, too, that snapback technology, that part that I described, we are going to bring that out in different voltage levels, so you will actually be able to get away with just using one TVS.
Got a few more questions on that TVS that let's go into. Scott, does the snapback TVS cause the system to have to reset versus a traditional clamping device?
No, they really operate the same way. The big difference is just the resulting clamp voltage that you get. So, for example, in this design, say you're operating at 48 volts and you get a transient pulse that comes in from the load. Maybe a traditional TVS might clamp it at 60, 65 volts, something like that. And again, this all depends on the type of pulse that comes in. But with that snapback technology, it's going to work the same way. It's just going to limit that clamp voltage to maybe 60 volts or even less. So it just gives you some more headroom between where you operate and where things start failing when that voltage gets too high. So hopefully I explained that well enough, but yeah, you don't have to worry about your system resetting. It's just a matter of how much that transient pulse gets limited.
And just one more question that I'm seeing with TVS in it here is a more general question here of why combine a TVS with a Schottky like we've talked about here.
Yeah, that's actually not a Schottky. I think maybe the circuit diagram makes it look like that. That's actually just a TVS symbol, not a Schottky. So like I mentioned, it's a bidirectional TVS and then a unidirectional TVS in series. And like I also mentioned, you can hopefully get away with just one, but if you need it in both directions, you just pick a bidirectional one. So that's really just I think a circuit diagram question. So hopefully that clears that up.
Okay. Next question I'm seeing here is how do you avoid a non-symmetrical current split during the switching process of a short circuit?
Can you run that question by me one more time? Yeah,
let me see here. How do you avoid an unsymmetrical current split during the switching of process of a short circuit? That's the word-for-word question there.
Yeah, if I'm understanding that correctly, hopefully I am. So you've got those 10 Mosfets connected in parallel, and then you get a short circuit of some kind on the load. And yeah, you're going to obviously get a ton of current that's going to, may or may not split equally. That is actually a good question. Obviously, they're not going to self-regulate because that, that pulse is quick before your system shuts it down. So kind of all bets are off there. Here you're going to kind of rely on the pulse capability of those Mosfets that I talked about. And when you use a bond wireless or a clip construction, that definitely helps compared to a bond wire, because a bond wire almost acts like a fuse. So if you put a high enough pulse through there, it's just going to burn that bond wire up. You got a little more forgiveness with a clip construction. So, yeah, probably one or two or maybe more of those Mosfets going to take some more of that short circuit current, but hopefully you can ride through it and until your processor recognizes it and shuts everything down.
All right, sounds good. Let's see here. Is there a 48-volt net standard, like ISO, LV, XX, anything like that?
Yeah, there is. I don't have the number off the top of my head, but yeah, for sure. You obviously want to stay below 60 volts. That's that safety threshold, which is why 48 volts was picked. Because, above 60 volts DC, you can still get a shock, believe it or not. So, yeah, there's definitely a standard where that 48-volt bus needs to operate. And I think it's, 59 and some change volts, as long as you stay under that 60 volts under normal operation. So yeah, that 48-volt standard for sure, you've got to follow that. And like I said, this is well established in Europe. There's already vehicles in production, and like I said, also it's making its way to the U.S. So yeah, you're going to definitely want to take a look at that spec.
Okay. Next question, Scott. Could a section of trace be used for current sense?
You know what? I've seen that done a few times, but typically it's done where you really don't need a lot of accuracy on your current measurement. So basically, yeah, you could use a very large trace on your circuit board. It obviously has some resistance to it, not very much, but that resistance is not going to be well defined, circuit board to circuit board. It's also going to change resistance values as the temperature changes. So I would not suggest using that for any type of control or protection. Like I said, if you want to get a rough current measurement, I've seen people do that, but I would not suggest doing that for, like I said, for control or definitely for protection purposes.
Got it. Another question that I've got here, Scott, how do you design the system to avoid inrush current when the relays are closing? And they're wondering if there are any particular resources that Vishay might have about this subject in particular, webinars, app notes, anything like that.
Yeah, I don't think we have any app notes on our website, but I mean, I touched on it a little bit. There is a pre-charge circuit in this design, and basically all you're doing is you're using a separate Mosfet and a resistor just to limit that current. So it's a pretty simple design. It's basically you're looking at an RC curve. You know, it depends how much capacitance you have in your load. As far as, you know, what you want to limit to or how long that pre-charge pulse has to be. But I think that's pretty well established in literature. You could probably look that up pretty easily, but it's basically just an RC curve that you're limiting until you get that capacitor charged.
Got it. All right, I think we got time for another question or two here. How much mitigation to arcing in a relay is achieved via the addition of capacitors across contacts?
Yeah, I'm not really a relay expert, but you know, I know there's ways to you know, mitigate that arc or, you know, keep it reasonable, but I also know those contactors or those relays, I guess you start calling them contactors when they get larger. They get pretty expensive when you start talking about arc suppression and maybe having a vacuum inside of there so you don't ionize the air. I mean, I've looked at that a little bit, but I think the bottom line is that there's ways to get rid of that, you know, that arc, but it gets expensive, it gets large, and obviously anytime you're talking an automotive application, you start talking expensive and large, and you're going to want to start looking at something else. So that's really the intent of using like a solid state relay, or we call it an eFuse in this case. So I hope that answered the question.
Yeah, I think so. Thanks. Now, I think we've got time for, I think one more question here, Scott. Can we transpose these different technologies for an HVDC network? You know, we're looking at 200 volts or higher. Is there the option to take what we're talking about here and transpose it into that application?
Yeah, actually, that's a good question. We're looking at that as well. It throws a whole nother set of problems in. So obviously you could use higher voltage MOSFETs, but then, you know, now that you're, you know, above 60 volts and you're up into the hundreds of volts, you have to look at all the safety requirements. So now you're talking about galvanic isolation between the primary and the secondary, you know, separating your 12 volt or your lower voltage circuitry from your high voltage circuitry and keeping it safe. So yeah, I guess the short answer is yes, it's possible, but you'd really have to redesign the whole thing. So it wouldn't be just a matter of taking this design and changing a few things and making it high voltage. So I hope I answered that, and I hope that's something maybe Vishay will be able to address here in the future, because that is a very common application. So good question.
And I think we'll do one more question here, and then we can wrap it up here at the top of the hour. And is this available to buy? Is the demo available for people to purchase?
Yeah, I've been asked that. I think there's a plan to do that. I don't think it's available right now, but yeah, I think that would be a good idea if we could have like a demo kit or a demo board, so you know, customers can play around with this technology. Obviously, you'd want to take this design and ruggedize it for, you know, for an actual application or build it into something else. But yeah, I think that'd be a good way to you know, just get something in people's hands to play around with. So let us check on that. We'll let you know, and you know, you'll hopefully see it on our Vishay website or in distribution if we decide to go that route. So thank you.
Great. Well, everyone, we're at the top of the hour here. That certainly was fantastically robust Q&A session that we had there. Thank you to our audience for being as engaged as you always are. And thank you to Scott Blackburn and to Vishay Intertechnology for joining us here today and going through everything that we've been talking about. Thank you so much, Scott.
Well, thank you. Thank you for having me. And yeah, if there's any follow-up questions, you know, get a hold of us at Vishay, and we'll try to help you out. So thanks again.
Perfect. Well, everyone, I've been Jason Montgomery, your moderator here for this session. Again, if you're looking for more excellent resources from Vishay, you can find other webinars that we've done with them on allaboutcircuits.com, and I certainly look forward to doing more with Vishay and hopefully Scott here in the near future as well. So thank you to everyone who's been here in attendance. This session is available on demand for you to watch afterwards. You'll get an email about that after the case as well. So thank you to everyone for joining us. Thank you to Vishay, and everyone stay safe out there and have a great day.
Thanks.